for resistance?
No, not in this context.
It's the ideal gas constant.
Yep. Universal gas constant.
Is that, are those related to each other?
I think so. Just when I was looking up earlier today, they called it the universal gas constant instead of the ideal gas constant. I have to look it up. Do you know what it is off the top of your head?
I know it starts with an A.
Yeah, we're in the same place there. 8.315 joules per mole Kelvin. 8.315 joules per mole Kelvin. All right. Little bit.
Is that the number of molecules?
Not the number of molecules. You went too far.
Particles?
Nope.
Number of moles?
There we go. That moles on the bottom there, they need something to cancel out with. So that's number of moles. You were just ahead of your time. What is big N?
Is that the number of molecules?
Or particles? Which is what we're working with here. And case of B. See what you'll remember from last Monday. Apparently not a whole lot right now. Boltzmann's constant.
So that's just the universal gas constant divided by Avogadro's number, right?
Yeah. .38 times 10 to the negative 23rd joules per kilogram Kelvin? No, just joules per Kelvin. All right, so we've got this for an ideal gas. So obviously we've transitioned from dealing with solids or substances in general, we were specifically doing solids, into dealing with gases. Standard temperature and pressure. Flashing back to chemistry.
Is that 0 Celsius, 100,000 pascals, and or that?
It's something along those lines. Oh, okay. 0 degrees Celsius. So temperature. Standard temperature, 0 degrees Celsius, 0. And then standard pressure, 1 atmosphere, which translates into 1.0133 pascals. So, oops, times 10 to the 5th pascal. So a little bit more than 100,000 pascals.
I feel like I remember it being, at least when I was told, that it was
Exactly.
specifically 100,000 pascals, like close to atmosphere, but not.
Huh.
Because I had a conversation with one of my parents, and they remember it being something completely different, not 0 degrees
I'm
Celsius.
wondering if it changed at some point. I'll have to look that up. I know that there was a shift within the past couple of years, redefining some of the standards. I guess you're looking it up right now?
until 1982, it was 0 degrees Celsius, 1 atmosphere. Since 1982, 10 to the 5th pascals, exactly.
Then I apologize.
At least that's IUPAC's definition.
And that is whatever.
Whatever Wikipedia says.
Okay. And the science stuff in Wikipedia generally is pretty good. So. Oh, question mark. All right. Well, thank you for correcting me. Thinking back to, we talked about ether waves, didn't we? That waves need a medium to travel through. So how does sunlight, this was the thinking, how does sunlight get from the sun to Earth? There must be some medium in outer space, so they came up with this idea of ether. And so that, was it you? I was talking with this group about that?
I don't.
Not sure.
I don't remember that.
You don't? Okay. So there was an experiment done in 1890s, the Michelson-Morley experiment, which basically was looking for ether. And this is not the same ether that they use for knocking people out to do surgery. This is an ethereal substance. And they did the experiment in the 1890s, and that's generally hailed as the one that showed that ether doesn't exist. I have a book from the 1940s, which still talks about ether waves, and referring to light, as if there needs to be ether in outer space in order for light to travel to Earth. So they were probably repeating what they had been told, and repeating what they had been told, and so forth. So with that correction, I will try to endeavor not to perpetuate the old way of thinking. All right, so we've talked about the fact that temperature is related to the average kinetic energy. However, that means some things are going to be traveling faster than that, some things will be traveling slower, or properly worded. Some things will have more kinetic energy, some things will have less kinetic energy. There's got to be a distribution. And so Boltzmann, along with Maxwell, came up with, they derived a distribution of particles called the Maxwell-Boltzmann distribution. I will not derive it for you, and I know you're sad about that. I'm close to being able to deliver how they derived it, but there's one piece that I keep getting caught on. So I'm not going to derive it for you. I'm going to just present it to you. Oh, where to keep that? This stuff's not. So there's something known as a frequency distribution. As a function of speed. And that is equal to 4 pi times the m divided by 2 pi kBt. To the 3 halves times the speed squared, then e to the negative m v squared over kBt. Did I lose a 2 in there? I did lose a 2. So as we're looking at a distribution of, we have these particles moving around in this gas, in essence, the distribution is gonna look something like that. If the temperature is cold, then it's going to shrink that way. So a colder temperature will look like, have a distribution more like this, and a warmer distribution it starts to flatten out. Which makes some sense, because with a warmer temperature, I'm expecting more particles moving fast, and so you take whatever number of particles you have, it would spread them out towards the long end. But what I want us to do, something that is in our wheelhouse, and then we'll take a break after we've done this. Not finding the average speed, but the most probable speed. So V and P for most probable. What is the most probable speed, assuming that that distribution is accurate? And it is. How would you go about solving it? Besides brute force. I have a function. We're trying to find the peak. The value of V that would produce that peak. What would you do? Hint, it's a math question. How do you find a maximum?
Derivative,
And then?
where that equals 0.
Yeah. So, we're trying to maximize F with this value of V that will produce the maximum F, so we take the derivative, set it equal to 0. And what's the derivative? Oh,
Okay, so do we need to do the product rule?
yeah, we will. This whole bit right here, the stuff in front, which does not have a V in it. Why don't we just call that some letter we're not using? We're not using C anywhere here. We're just gonna call that C for a constant. All right, so we have some constant times product rule.
2v e to the negative mv squared over 2kbt plus is the negative mv squared coming out?
Okay, well, sort of. Plus V squared times.
Yeah, and then
So what's gonna be popped down in front from doing the derivative?
Derivative of the inside,
Okay, which is,
mv over kbt negative.
The two comes down and cancels out with the 2 that's already there. All right, then times the derivative of e to the something.
Which is just e. Did the same something.
Okay. Negative mv squared over 2 kVt. All right. So the product rule, have z equal to 0. Obviously, constant cancels out. That's why the details of that did not matter a whole lot. So we're left with setting this equal to 0. Fortunately, we have, right, so that cancels out. Fortunately, we have this term right here, which can cancel out, so we divide everything by it. And I can get rid of the v. So what I am left with is 2 equals, since that's negative, take it over to the other side, v squared m over kVt. Since we're trying to find the most probable speed, solve for v. Uh, 2 kVt divided by m and then square root. Went too far. So we have the most probable speed. We're gonna take a small little break here. We're gonna come back and we're gonna now find average speed. If nothing else, an exercise in calculus. The physics of motion. So let's talk a little bit about this frequency distribution. Just stick with one of the curves. So for a particular temperature, we now have that value right there, so the most probable speed. What a frequency distribution basically is telling us is the fraction of the particles that are at some speed v to v plus dv. So I take a small little wedge of this and tells me the fraction of the particles that are going to be within that small range right there. So I know that if I wanted to find an average speed, what I need to do is to add up all the speeds and divide by however many particles I've got. But when I'm dealing with 10 to the 23rd level particles, not particularly easy, and I need to take advantage of this distribution. So the number of particles that are in that little wedge right there, so this is the number of particles with speeds from v to v plus dv. Well, it should be directly related to the number of particles there are, times the fraction of the particles in that region, or in that range. Range is probably a better word. Times the width of the range. Well, we can now narrow that down. The fraction of particles that's in that range is just my distribution function as a function of the speed times dv. And then I got the n up front. Let's see. So, my average speed should be, well, the total number of, I guess, the sum of all the speeds divided by the number of particles. That's a generic. Which would be at a particular speed, how many particles do I have at that speed? And let's face it, we're going to an interval here, over n. And this function right here, let's just accept that dn is a function of speed, and I don't have to write that, the functional notation there. I know what dn is over there, so I got the integral of speed times n times the fraction of particles as a function of v dv over n. N's cancel out because it's the number of particles that I have. So what I'm left with is the integral of v f dv, where f is the distribution function, frequency distribution function over there is a function of v, and this is just speed.